We should be live at this point. I think. We'll see what happens. Someone has to say hello. And then you all have to say hello. And then, of course, we can do this, too. Let's just go live. And I can just go to the browser.
And they are tracking no issues. You can see it is beautiful, clear skies at Kennedy Space Center. Weather will not be a constraint for today.
There you go. So I'll be just like watching the SpaceX launch just in another window, and if you know, if it happens. But actually, the way this tends to work is people will have to let us know that the launch is happening because we're busy. We're working on a thing. John wants to know where your fern is. Paul, you're at the office, right?
I am at the OSU Steam Factory, which is a space downtown away from main campus that's available for members of the Steam Factory, which is science, technology, engineering, arts, and mathematics, to use when they don't feel like being on campus.
There you go.
Yeah, sorry, my fern's at home where it belongs, but there's Steam Factory.
That's really cool.
Yeah, it's a really cool space.
Yeah, so by all means, let us know what happens. But I think if everything goes well, this Bulgaria sat is going to be the second reused SpaceX first stage booster, and it's supposed to land, and it's going to be a tough one because it's a much more aggressive orbit. So the chances of them being able to get this rocket back are slimmer than normal. All right, I'm going to say hi to a bunch of people. Marcel and Albert, just so you understand what's going on, we kill about the first 5 minutes, and then we actually get into the show. So that's what we're doing right now. Is we're just making sure that everyone gets in, gets seated, says hi to me, and then we will actually start the show in about 3 more minutes. But we are live, so normally I prep people for that, but I totally forgot. Anyway, the other thing is we're redoing all the windows in our house. So we got a new window, and here I'll switch to my my main screen here. It's actually better in that other one. Anyway, so you can see these stairs here, and we have a rat that goes up and down those stairs. So if you notice, if someone spots the rat going up the stairs, he's looking for bird seed on our deck. All right, here we go. Hello to Adam Synergy, Astro B, Bill K, Bort Klankar, Brian Stab, Brian Yoko, Capital H, Carolyn B, Celia Lawler, Seaman, Chitranjan Baghi, Colin Jones, Connor Lennon, The Hooded Crow, David Dunn, Dynamo Dan, Ilad Avron, Galaxia, Guido Bibra, Helg Bierkog, Hugo Burnham, Elcan 1, John Gallant, John Seffel, John Victor, Karen Hutchinson, Lillian Brennan, Linda Sadek, Matt Minter, Mike Doman, Nancy Graziano, Peter Quinn, Phil Wilcox, Philip Berthus, Philo Sage, Arin Stroh, Rachel Fry, Richard Hayes, Rick Schwartz, Stephen Hawkins, The Goat, Tommy, Don Van Vand, Toxis, and Vanessa Romanello. Hey everyone, welcome to the Weekly Space Hangout. And we will get started in about 1 more minute. Rocket still hasn't launched. Here, let's just make absolutely sure. There it is. Not launched. All right, but like I said, I'll keep an eye on it in the corner of my eye for this entire episode. All right, I'll switch you guys away from the Brady Bunch mode. Full screen. On to me. Leonard is wondering why my window is reversed when not full screen. I actually have 2 cameras. So I have this camera, and then I have this camera. And so this is the camera that the guests can see. So that's what's going on. Filberthus. I'll get it. All right, let's get started. All right, here we go. Hello, everyone, and welcome to the Weekly Space Hangout for Friday, June 23rd, 2017. It's with a heavy heart that I tell you that this is the final episode of this season of the Weekly Space Hangout. So, as you probably know, we're going to be going on hiatus, on vacation, and we will be returning, I think, tentatively for September 8th. This week, we are going to be talking about a dead galaxy found by Hubble. Lisa is on, and NASA releasing a huge catalog of planets. Joining me this week to send off the Weekly Space Hangout into its summer hiatus is my good friend, Dr. Paul Matzetter.
That's me. And you know what? You're my good friend too, Fraser.
That's fortunate. It would be really uncomfortable if one
I feel like we've really bonded.
If one of us hated the other one, that would be, that'd be trouble.
We're way more amusing.
Well,
times the views.
We'll find out what happens after we come back from a week in Iceland, taking photographs.
I am not rooming with you.
That will test the friendship to the limit. You know, one of us might just come back broken. So
there can be only one.
We've got you're the regular, but we've got some special guests this week to talk about asteroids, and there's two separate people. So let me see if I can figure out how to make this come together. We've got Marcel Pescu.
Hello, everybody.
And we've got Albert Falk.
Hello, that's me.
Welcome to the Weekly Space Hangout. All right, so Albert, I'm gonna let you go first. Why don't you tell people sort of who you guys are, and what you do?
Well, we are from the NEOShield-2 project, which is a larger project consortium in Europe. We have done, let's say, a large activity in a couple of years ago, addressing science and technology aspects in order to prepare for the deflection of hazardous asteroids.
Right.
There are a lot of work items where we all together work. In the next minutes, I can maybe explain a bit more about these specific topics.
Right. So just to be clear, you guys are with the NEOShield-2 project, and this is out of Europe, and your goal is to save us all from an asteroid strike, right?
Yeah. Let's say we are doing a large contribution to the overall asteroid deflection community. This is, let's say, the largest project financed by the European Union in this context, and we are doing our best to play off some pieces in order to get rid of hazardous ones.
All right. So before we get on to what you guys are your specific project, can you sort of set the stage and sort of help us understand what are the risks? What is buzzing around out there that we should be aware of?
Well, maybe a lot of you will already know there are a lot of near-Earth objects around Earth on potential collision courses. A lot of them are known already, but much more are still unknown. And the larger ones, I guess, are mostly known, but the small ones, which are still large enough to kill an entire metropole or another larger city, are not yet known. And it happens quite often that in a short time frame, a new asteroid will be or is discovered. And then in some very busy nights, the astronomers do a lot of good work and calculations and find out, okay, this one is coming close, but not close enough for a real threat to the Earth.
We always report on this with Universe Today, where we'll like say, astronomers announced that a new asteroid just flew in between the Earth and the Moon. Oh, and by the way, we discovered a new asteroid, the one that just flew in between the Earth and the Moon. That often when they make that first close flyby, it is also the first time we ever even knew about them.
Sometimes, yes, you're right.
So, Marcel, how many of these objects, of that breakdown of the ones that are known, what percentage of them are unknown right now?
Well, that depends on the size. If for the largest size, it is probably that we know them all above 1 kilometer. The situation it's worst when we go to lower size, especially below 300 meters. Up to now, we know more than 16,000 near-Earth asteroids. Some of them are about 10% of them are cataloged as potentially hazardous asteroids that may pose huge damage to our civilization.
And just to give people a sense of scale, right? The one that hit Russia a couple of years ago, the Chelyabinsk meteorite, how big was that object?
That object was about 20, maybe 30 meter diameter.
Right.
But 100 years ago, 30 June 1908, it was the Tunguska event when the object was between 60 and maybe 200 meters, something like that. And the damage was much huge. Such objects can pose a problem to a regional problem.
Right. Okay. So really, it's that risk. So the larger than the Chelyabinsk, and then smaller than that 1 kilometer, there's this vast gulf of asteroids that are out there that we don't know where they all are, and we really should want to.
Yes. And that it is difficult to find them because when they came close, you need to observe them. And after that, you are losing them. They got fainter and fainter. And besides that, you also need to understand their physical properties. Are they just chunks of metal, iron, nickel, or like a rubble pile structure? You need to think of that.
Albert, so let's talk about sort of detection and then eventually defense. What is sort of the way that we're, with what you're doing with NEOShield, how are you looking to find and eventually protect us from asteroids?
Well, basically, we are not really detecting and discovering new threats. Our goal is more to revisit with a telescope already known objects and, let's say, characterize them by their physical properties. So we are doing infrared observations, spectroscopic observations, light course measurements, and so on. The goal is to get a broader database on available objects, especially in this small area between 50 and 300 meters, where the data is very, very sparse. So right now we have already doubled the size of the literature for these kind of objects. And that's already let's say, great contribution, which helps in future to identify whether this object with the known brightness will be a threat to Earth if it hits or even not. Maybe it's bright, but it's maybe not large enough and maybe not dense enough or heavy enough to cause a larger threat to Earth than the Chelyabinsk event. And that's the kind of information we are trying to gather and specify with the project.
And that's still fairly unknown, right? That we don't really know I know that astronomers, when they do, say, for example, the Torino scale, when they are estimating the potential damage that an asteroid might do, there's still a lot of unknowns about how these asteroids move and how the sunlight is changing their trajectory and position and how their orbits interact with the Earth. So what will sort of these new observations help us be able to understand?
Basically, the behavior of an asteroid on a possible deflection attempt. That's something we are addressing in very large detail. So we don't know really how the asteroid might react on a deflection attempt, whether it will break up, for example, or where the level of breakup energy is. We really want to know this because our goal is to deflect it by not breaking it up, by just pushing it a little bit out of its course without increasing the risk by breaking it into millions or even hundreds of pieces, which would mean a much higher threat to us, because 100 pieces cannot be really controlled afterwards. So we want to keep it as one part, and this level of energy which is necessary and should be avoided to keep this is one result of the simulations and modelings we are undertaking.
So Marcel, can we talk a bit about what kinds of technologies and strategies, you're talking about potentially doing some kind of a deflection. What are some of the ways that you'll actually do these deflections?
First of all, we need to understand them, what they are made of. And for that, spectroscopy is one of the powerful tools, because it connects the physics that we have in the laboratory with what we observe on the celestial objects. So one of our first goal from observational point of view was to characterize a sufficient large sample in a reliable manner with well-defined methods. We succeed to do that for 170 objects. That means we double this on this scale. So we saw that we have a wide compositional diversity among them. We saw that on smaller objects, we may encounter rare types more often than for the largest one. For example, we may have olivine-rich objects. We may have objects that are remnants of the comet's nucleus. And we can see that from the spectroscopy point of view. Also, photometry and light curves allows us to tell what is their shape with sufficient observation. Sometimes they are also observed by radar, but this is difficult.
But I mean, like, the sort of the traditional idea is to just like shoot a nuclear weapon, send off the Earth's arsenal of nuclear missiles at the asteroid and blow it up, or send Bruce Willis with a bunch of miners to try and dig into it. So I mean, what is probably going to be the most effective way to shift the position of one of these asteroids?
Well, that depends a lot on the structure. If, for example, you have a chunk of metal, a kinetic impactor will work perfectly. But if you have a rubble pile structure, a lot of boulders gathered together, a kinetic impactor will go through it. So the method you are choosing to deflecting, it depends a lot on the moment you are discovering and on its physical properties.
So you said, like, for a metal one, you send the world's arsenal of nukes at it, no problem. But for these rubble piles, that is definitely a problem. I mean, that's the vast number of them out there, right? Is the rubble piles.
Well, we have much other options we might choose. So in the most cases, we expect that, or in the most likely cases, we expect that we will discover a possible threat decades beforehand. And then there's much time to use a slow push method, for example, which also works very fine for rubble piles. This is maybe the gravity tractor mission or something called Ion Beam Shepherd, where basically you use a very small and very tiny momentum transfer between the spacecraft orbiting around the object to move it from its course over, let's say, 5, 10, 15 years, which is quite fine. For larger chunks of rock or even iron, impulsive deflection attempt might be necessary. And that's could be done by just a kinetic impact with a very high velocity and a high mass. That's sufficient for larger objects like 300 meters diameter, for example. And then if it really gets worse for us, then maybe we need much more energy, which might require hundreds or a couple of kinetic impactors, or even let's say a nuclear device, which is maybe not what might be possible in the near future given the political constraints.
I mean, you know, talking about the political constraints, the fact that those kinds of weapons, you know, we don't want that class of weapons at our disposal because they could be used for other purposes. Is that sort of the concern for war?
Maybe you can repeat the question.
Well, just wondering, like, you know, like to have weapons that powerful, able to help impact an asteroid, there's reasons why we don't want weapons that powerful here on Earth in the hands of governments or anyone, right? That's all.
Right. And there's also the International Space Treaty, which absolutely forbids these kind of weapons in space.
Yes.
So right now, we can't use them.
Right.
For, let's say, Earth protection activities.
Yeah, and like half the Outer Space Treaty is all about don't shoot nuclear weapons into space, don't test your nuclear weapons in space, just don't, right? That's that's what it's all about, really. Is you know, they didn't want each other to be setting up orbital nukes and shooting them down at each other, which would be pretty bad. And it's understandable. I can see that. So let's talk a bit about sort of the political will right now as you see it. Let's say that you are successful and you do come across some potentially dangerous objects that are out there, and maybe ones that are even just willing to test on. Do you think that there is the political will to gather together and try to make these objects safer for us? Is that there right now?
Safer in terms of getting them out of the potential collision course?
Yeah, like let's say that one is found that has a high, you know, it's high up on the Torino scale. Let's say it gets to the 4 or the 5, you know, that it's a smaller object, something in the 200 meter range, but one that has a very high chance of impacting us. Do you think that the world can unite to deal with this?
I think so, yes. And I also believe that it's not only, let's say, one team which is doing one deflection attempt. So we need redundancy on mission level. There will be a couple of missions built in several spacefaring nations, which will then launched in a more or less same time interval, and then will perform a deflection attempt. But before this will be undertaken, I'm pretty sure there will be also a reconnaissance mission in the years before to clear and clarify to a much higher precision the asteroid orbit and identify how large or even how low the potential collision risk might be.
I mean, right now, we don't even really know what the, you know, what of our various strategies would move, say, that rubble pile. That is it going to hold together? Can you even shift it? How much energy? And so we don't even know what scale of mission would be required to change an asteroid of a certain size. So I mean, do you feel like that question is going to get answered soon, that we're going to know what it takes to move an asteroid?
I think it's answered already. There are a lot of pre-studies undertaken all over the world in the last decade. So we can constrain the minimum and maximum energy or power which need to be transferred to the asteroid in order to get it out of its course. But of course, there are still a lot of uncertainties on the impact physics, for example, but as well on the technology itself, which hasn't yet been proven in a, let's say, realistic environment. So the technology must be developed and demonstrated in space. And that's the reason why we really need a demonstration mission, hopefully in the next decade, which will then enable us to build up a viable deflection capability.
Just got a couple of questions that have come in from the people watching. This one comes from Arjone. Could meteors in time be deflected by low power lasers? Can we use lasers to move asteroids?
good question. Well, I think we would really require a very high energy level for the laser on the Earth's surface, which needs to be concentrated over a very long distance and needs to be guided and fixed to the meteor's position over a longer time span. Seems to be very, let's say, critical or at least difficult. I'm not sure whether technology in this context is already at this readiness level, but I'm no expert in this context, to be honest.
Yeah. So Marcel, over the next few decades, if everything goes as you hope, what kinds of advancements, what kinds of discoveries do you think that we'll be making to kind of push this whole effort forward? What do you hope for?
First of all, we need an automatic survey, more automatic survey, like the one that will be brought by the new robotic telescopes. This will allow us to track their astrometry, because the position, the precision on which we are able to calculate the orbit depends a lot of this astrometry. And our integrations allows now just for 100, maybe several hundred years to predict their position, but in time, we don't know. Also, we need to understand their composition to get more physical data about them and to be able to categorize them and see what is the proper measure to deflect them, because it depends a lot for the moment when it's discovered, when it was discovered that is on a potential course. Also, it depends on its composition. These advances will allow us to better defend our planet. So it's all about knowledge. We need to know more about them.
I guess one last question for Albert. Do you think that we're taking this seriously enough? Do you think that we, the public, the governments, do you think that they are stepping up and sort of taking the right action to be prepared for some kind of asteroid impact?
That's a nice question. I think it's all about statistics. If we look into the statistics of larger asteroid impacts on Earth, we have plenty of years to build up those needed technologies and scientific answers. But statistics are not real. It could be that there will be an asteroid threat discovered the next week, which will impact in 4 weeks, and then it might be too late. Or even if we are discovering something impacting in 3 years, that's already a very, very high and demanding challenge for industry and scientists on Earth. So it would be better if politicians would spend more money in the right preparation stuff. But as those people always, let's say, think in legal periods, how long they are elected and how much money they can spend for those topics, it is difficult for us to give this very important topic as much, let's say, importance as it would require. So it's always necessary to keep going and also to increase the public awareness about the threat imposed by near Earth objects. And that's what we are trying to do so.
Right.
This gives me the chance to emphasize the next week's activity, which is the Asteroid Day on June 30th.
Oh, so, there you go. Asteroid Day, June 30th.
Yes, maybe you are already aware of. This will be a very, very big day for all the asteroid community all around the world. There will be plenty of local events and a lot of online activities ongoing. And yes, we are also participating, supporting the overall goal of increasing public awareness and getting everybody in the boat to promote and push for better activities and improved activities to prevent and protect the Earth.
I got one last question here that comes from Refugio and Acro, which is how much more money would it take to get reasonably prepared? So if you could make the governments do what you wanted, sort of how much more of a magnitude of what is currently spent on asteroid research and defense should be spent? Blank check. I'll just write it. I'll write a blank check right now.
It would be good.
Yeah.
No, I think if I heard about that the budget of NASA for the asteroid coordination center is something about 50 million a year, which is already quite a lot. And I think NASA or the United States are very well prepared. But in Europe, there's nearly nothing which will be paid in this context. There are a lot of scientists working for, let's say, smaller projects, which can dedicate some hours and some weeks for these activities. But this is far, far away from 50 million per year. And I would say to increase the deflection capability of humankind, something like 50 to 100 million per year, and not only in the United States, but by a couple of spacefaring nations with the required experience and heritage might be a good choice.
And that's not very much money. I mean, 50 to 100 million dollars is the cost of one rocket launch, if that. I mean, the SpaceX launch that we just saw, they run for about $100 million. So,
well, but then there will be also the cost for a deflection demo mission, which will be much more.
Which will be much more, yeah. All right. So, Marcel, Albert, where can people find out more?
First, the NEOShield project website is very well maintained. So NEOShield.eu is the best address to go for. You will also find our profiles on Facebook and Twitter. Twitter is @NEOShield-team, and on Facebook you will find it when searching for NEOShield or NEOShield-2. And then, very important for next week, please also check out asteroidday.org website, and you will also find Facebook and Twitter profiles. There will be a lot of events going on and with much more information all around.
Fantastic. Albert, Marcel, thank you so much for joining us on the Weekly Space Hangout this week. And good luck. We're counting on you to keep us safe.
Yeah, thanks a lot, and also for the invitation. It was a quite pleasure to take place here.
Let's see, get Marcel there.
Thank you also.
Thanks, everybody. All right. Well, that was cool. I feel safer already. Let's move on to the next segment of this episode of this very special final episode of the Weekly Space Hangout for this season. Just this season. So, Dr. Paul, Matt, Sutter, we're going to be talking about a bunch of stuff today. How you doing there?
Want to start? Yeah, the whole universe is going to blow up.
in like a few Google years.
If phantom dark energy is a thing, then we only have like half a dozen billion years left.
Perfect. Well, all right. So let's get on with the stories today. Let's see. What do I want? Okay. Well, let's talk about that dead galaxy.
Yeah, this is weird. So we've been peering ever further back, closer to the Big Bang. We've been looking for stars. We've been looking for the first stars. We've been looking for the first galaxies to appear. And what we're finding in general over the past few years is kind of surprising us, because we're finding mature galaxies. We're finding mature stars very early on, and this is another case. This is a galaxy that looks a lot like the Milky Way. It's a disk galaxy. It doesn't have spiral arms, but it is a disk, and it's relatively dead. It's only full of old red stars. It doesn't have any new star formation. And this is weird for two reasons. One reason is, what is this old galaxy doing at a relatively young epoch in the universe? And two, galaxies chew through the material. They age really fast when there's a lot of collision. So we generally see older dead red galaxies as ellipticals or irregulars. These are the consequences of galactic collisions. When a galaxy is left by itself, it forms a disk. But when it's left to itself, it can keep churning out new stars year after year. So it shouldn't be dead. So we're seeing a dead disk galaxy, which is really weird. And we're seeing it in the early universe, which is double weird.
I mean, one of the things that we think about is, that we're living in the coolest time in the universe, that now is the party. But actually, the party's long over. We came very late to this party.
Oh, yeah. The lights are already getting shut down in the universe. Peak star formation happened, what was it, 3 billion years ago? I don't quite remember the number off the top of my head, but it was in the past. We're already in the wind down phase of the universe. But here is an observation that very early on, when galaxies were just starting to become a thing, there's already a population of over-the-hill ones.
How early do we think that life could have formed in the universe itself? Is it possible that a galaxy like this might have been able to get life going very, very early on?
Yeah, that's a good question, especially life like ourselves that requires carbon and phosphates and all sorts of these heavily processed elements that require multiple generations of stars before you can start building rocky planets with water on their surface and blah, blah, blah. We used to think that we do know it takes multiple generations of stars to build up those elements, but we thought it was pretty spaced out, that there was the first generation for a while, then the second generation for a few billion years, and then you get to us, the solar system forming 4.5 billion years ago. But if there's already dead galaxies very early on, within the first few 100 million years, that means there's already been a lot of processing. There's already been multiple generations of stars. Maybe, and this will require some more observations, especially with the James Webb Space Telescope, maybe there's already enough heavy elements back then.
And I think that's really, you mentioned with the James Webb Space Telescope, and that's a good point. Like, this galaxy was discovered thanks to a gravitational lens. So the only reason that the Hubble Space Telescope, the most powerful telescope that we have at our disposal right now, could even see this galaxy was because there was some kind of dark matter haloed galaxy cluster in the way, and it was a bank shot of the light. And so, I always say we don't know what dark matter is, but we know how to use it as a telescope.
Right. Yeah. You have the bending of space-time acts like a lens. It can bend light and it can magnify images, just like a normal glass lens can. And so, a bank shot, slingshotting, those are all great terms to describe where we're looking farther than we really ought to be able to.
And we only get to see that when you get these alignments of galaxies.
Super light.
And so one good reason to be excited about James Webb, which is now only a year away, is to be able to brute force see this stuff directly. So it's not
stare right at these galaxies.
Yeah, so it's going to be looking these kinds of examples. So we don't know if these are common or rare.
Yeah, exactly.
Because we just don't see a lot of them. But once James Webb is up and operational, we're going to be able to see them. We're going to be able to do proper surveys of these things. So it's a whole other world. So if you weren't already excited about James Webb, it's time. So
it's coming.
It's coming. All right, let's talk about the next story that we've got on our list, and this is all about LISA. And
LISA, the Laser Interferometer Space something. What does it stand for?
Observatory? Laser Interferometry Space Observatory?
Observatory with an A? That's weird.
LISA. Oh, no, you're right.
LISA.
Experiment. Hold on.
Experiment. Is it French? I have no idea. I totally blanked on what it stands for.
Yeah, someone's going to tell us.
I know it's laser. I know it's interferometry.
Yeah. Anyway.
Laser Interferometer Space Antenna.
Antenna. All right.
Because LISA.
I'm sure like all of the commenters are like, it's antenna, stupid.
It's antenna. No, it's antenna. Sorry. It's a go. It's happening. The European Space Agency is ponying up the cash, and they're going to start designing the mission now. It won't launch until 2034.
Yeah.
So they've got some work to do between now and then. But this is the big brother or big sister to the ground-based gravitational wave observatories, where coming online soon will be Virgo. So we'll have 3 on the Earth, and those are going to keep cranking out results in the next couple decades. But they're only limited to a certain slice of the gravitational wave spectrum. They're only sensitive to a certain range of frequencies. They can only see certain kinds of physics happening in the universe. LISA broadens that view, it complements that view. So LISA is going to be able to see supermassive black holes when they eat stuff. They're going to see more spirals and mergers. They're going to get to see stuff falling in, spiraling into these massive black holes. They're going to see potentially some gravitational wave signatures from the Big Bang itself. That's a question of how strong those signatures are and how sensitive LISA turns out to be. But it's one by one opening up these windows to the gravitational wave universe.
And just for a comparison, the LIGO instrument, which is the ground-based one, there's the 2 detectors in the United States. They have arms that are, I think, 4 kilometers, but actually there's a laser that bounces back and forth, and it makes an effective length of about 10,000 kilometers, I think. Anyway, these are going to have a arm length of 2.5 million kilometers. So these 3 satellites are going to be flying in close formation. They're going to be sending their laser pulses back and forth between the 3 of them. What does 3 give us over 2?
3 allows you to pinpoint a direction. So the ground-based ones that just have 2, you can get a sense of the direction, but you need to add in another instrument or a third instrument to actually get the precise coordinates on the sky of where that signal came from. But because there'll be 3 built into LISA, they'll be able to triangulate positions and get at the positions of these gravitational wave sources. And this is, to say this is technically challenging is a mild understatement.
Yeah.
There was an entire space-based mission called the LISA Pathfinder, which just recently completed, just to test one component of the full LISA mission. So we already spent hundreds of millions of dollars just to see if it was technologically possible to do it 2 decades from now.
Right. So to test if you can like maintain the position of the satellite and be able to send and receive transmissions at the level of accuracy that's required, they did a whole mission, and its job wasn't even to detect gravitational waves, just to test if they could do this from an engineering capability.
Yeah.
Now let's talk a bit about, right now the kinds of gravitational waves that are being discovered are these mergers of intermediate mass black holes. And as I understand, it's really because they're massive enough and yet moving fast enough that the detections are even possible. We can't detect the stellar mass black holes merging, and we can't detect the supermassive ones merging because it's just too slow. So what's on the menu when LISA gets operational? You mentioned, you ran through a bunch of things, but let's talk specifically about some kinds of things we can get our hands on.
And it's just like how hearing works. If you want to hear something, it has to be loud enough, and it has to be in the right frequency range. If I blow a dog whistle, it's loud enough to hear, but my ear isn't designed to pick up those kinds of frequencies, so I'm not going to hear it. Same for a very low rumble. I may feel it through my body, but my ears can't hear it. LIGO and the ground-based detectors are only sensitive to certain frequencies of gravitational waves, and those sources have to be loud enough. So they don't get to see small black holes colliding together because they're not loud enough and they're not in the right frequency range. And we happen to get lucky that these intermediate mass black holes of dozens of solar masses turns out to be rather common, which itself was kind of a surprise that allows instruments like LIGO to detect them. LISA will be tuned to a different set of frequencies. So it's going to look for the monster black holes, the supermassive black holes in the centers of galaxies. As matter falls and spirals into those supermassive black holes, That will stir up space-time. There'll be a specific gravitational wave signature that LISA will be sensitive to. As these massive black holes, when galaxies collide and the supermassive black holes coalesce and collide at the center, LISA will be able to pick it up. LISA will also be able to see compact binaries like neutron stars merging together at a very rapid rate. And then perhaps most intriguing at all is these hints from the Big Bang itself.
Right. And could we talk a bit about that? Because, as I understand right now, the cosmic limit for what we can see is the cosmic microwave background radiation. And that's the radiation that, like, the first time light could move freely in the universe. And we can't see beyond that. So how will gravitational waves allow us to go beyond the cosmic microwave?
Right. So the cosmic microwave background was generated about 300,000 years into the history of the universe, when the universe cooled down enough that the first atoms could form, and it transitioned from being a plasma to being a neutral gas. This allows light to travel freely without hitting any other atoms. Some of that light has traveled for 13.8 billion years until it hits our radio and microwave detectors. And we're bathed in this radiation. We can see it in every direction. That's the equivalent of a baby picture of you when you're about 7 seconds old.
Right.
So that's like, so imagine that's our earliest picture we had of any human or any animal. Say you're trying to figure out how an animal develops and is born. And the youngest picture you have of that animal is at 7 seconds. So when we want to study earlier times, right now we're limited because we can only make a guess about what's going on in the earlier universe, see how that would impact the cosmic microwave background, and then look for those signatures in the cosmic microwave background. With this technique, we've made a lot of progress. We have learned a lot more about the early days of the universe because it gives a signature, it gives an imprint in that first image. But this is an indirect measurement. It's not going to take us farther than really where we are now or 10 years from now. There's just not enough information in the cosmic microwave background to answer all the questions we have about the early universe. But gravitational waves, if the universe is doing some messy stuff, it's going to stir up space-time in a specific way. Those gravitational waves will propagate throughout the universe until they hit our LISA detector.
It's sort of, I'm trying to imagine what that could look like. What could the universe interacting before the cosmic microwave background radiation, would it be kind of, because there's no stars then, like literally the entire universe was still too hot, it wasn't as hot as a star anymore. That was like the first 15 minutes after the universe, but it's, still really hot. What would it be doing? Like, would it be reverberating from its formation, from its expansion, watching Netflix,
drinking milkshakes,
jiggling around? Like, I'm trying to imagine.
Yeah, you're absolutely right. Before 300,000 years, the universe is a hot, dense plasma. Like think of the interior of the sun, where it's so hot that atomic nuclei are separated from their electrons and they're just all bouncing around like crazy. So you've got matter that's really hot, and you've got tons of radiation. And the radiation is hitting the matter, and the matter is hitting the radiation. It's a hot, dense, messy soup. In that early universe, there are vibrations. There are pockets that are a little bit hotter or a little bit cooler, just little variations. And we see this in the cosmic microwave background itself. We see the state of the universe as it was just 300,000 years in, where there are these pockets of slightly hotter, slightly cooler. They're all complex and interleaving and reverberating out off each other. There's literal sound waves. Sound waves are pressure waves. There are pressure waves reverberating throughout the early universe. and we see their imprint in the cosmic microwave background. But those sound waves, those reverberations, also make an imprint on the structure of space-time itself. And by listening to that, we can reconstruct the internal state of the universe when it was very young.
Now, if Lisa, I mean, this is still, you know, in the maybe category, but there's another mission in the works coming down the road, which is called the Big Bang Observer, and this takes Lisa and multiplies it by 4. So you would have this constellation of 12 spacecraft flying in formation, and in theory, this is going to have the detection sensitivity to be able to make
so remember, there's 2 things to hearing. You need to be in the right frequency range, which Lisa will be for these Big Bang observations, but you also need it to be loud enough to actually hear. And there's varying models with various levels of nuance and detail about what went on in the very early universe. Some of these models are pretty optimistic and show that space-time may be banged pretty hard and something that Lisa might be able to pick up. Maybe not. Lisa may not just have the sensitivity to detect these very, very faint signals, so we need a more powerful instrument. Just like you would need a more powerful telescope to see a fainter star.
Right, yeah. But still, I mean, the fact that Lisa's getting developed, I mean, space is the place for this kind of instrument. I mean, I think that the work with LIGO, and there's a Japanese version of this and the European version of this, and they're putting an Indian one in place as well. These are all a prelude to space where the real detections are going to get.
They work together, actually, because Lisa, the frequency range, it can't see stuff that the ground-based detectors can.
Right.
So they're going to work together, just like ground-based observatories work together with space-based observatories.
Oh, you're such a politician.
I'm nice to everyone.
All right, well, we've got just a couple of minutes left, and let's just talk about this. Now, we had some advance notice of this, which was that we had Dr. Natalie Battaglia last week telling us about how there was going to be a big sort of update from Kepler on Monday, and we're like, is it going to be Earth 2.0? And she seemed a little vague. Turns out it's not Earth 2.0, but tons of new planets, including 10 in their sun's habitable zone.
So it's not one Earth 2.0, but it's about 10 Earth 1.4s.
Right, 1.4.
Close, not quite ready for release yet.
Yeah,
but it's still in beta. I believe, is this going to be the last Kepler data release? I think it might be, but I'm not sure. But either way, it's hundreds of new planets, including 10, a little bit bigger than Earth, but in the habitable zone of their star. So there's 2 main results from this catalog. One is, hey, more Earth-like planets. Just how common are these Earth-like planets? Turns out they're pretty common. And 2, we have enough data now where we have thousands of exoplanets, where we can start to do some statistics. We can start to see if there's populations of planets, where we have enough data, enough raw numbers, that we can say there are different kinds of planets. And an interesting pattern is beginning to emerge. It seems that the cutoff size for rocky planets like the Earth is about 75% more massive than the Earth. Like, solar systems can form, they build rocky planets, small planets like Mercury or Mars, bigger ones like Venus or Earth, even bigger like the super Earths we're detecting. But once you get to about 75% more massive than the Earth, you don't see any rocky planets anymore. Instead, you start to see gas giant planets. You see some smaller versions of Neptune, and then up to Neptune size, and up to Saturns and Jupiters, and bigger than Jupiters. There seems to be this divide between rocky planets and gas planets. We're not exactly sure what's going on.
Yeah, the total number now is 4,034 planets from Kepler. And
planet candidates, yeah.
Yeah, of planets. 2,335 have been verified as exoplanets. 50 habitable zone candidates have been found, and 30 have been verified. So that's just phenomenal. It's an enormous amount of data. And
everyone gets a planet. You get a planet.
You get a planet. Everybody gets a planet.
It's a planet.
Dr. Paul Metzetter, what are you going to be doing over the summer?
Well, I am going on vacation, which is going to be nice. And I am, what am I doing? Probably
Eclipse.
Working. Oh, yeah, there's the eclipse. I'm going down to Nashville.
Yep.
Where are you going to be for the eclipse?
We're going to be in St. Louis.
Nice.
Yeah. So, and we've got a whole hotel rented and
whole hotel?
Whole hotel. We've rented a bunch of just for me.
Just for you and your entourage.
Yeah, my entourage. Yeah, no, just me, Pamela, and our 200 closest friends.
Nice.
So yeah, we're gonna be we've got that going, and then we've got a couple of buses that we're renting, and then we're gonna sort of chase the eclipse depending on what happens with the weather. If we're lucky, we just have to drive about 10 kilometers, and if we're unlucky, then we may have to go a few hundred depending on where the clear skies are.
Yeah.
I'm actually this is the last week of this season because next week I will be in the wilderness of Oregon chasing various flora and fauna with my wife and her nature photography buddies. So we're going to be going after birds and bugs and yeah, it's going to be pretty epic. So that's going to be a thing. We're going to do some astrophotography as well while we're in the mountains of Oregon.
Nice.
Yeah, and then apart from that, now this is it for the Weekly Space Hangout and Astronomy Cast. They'll be back in September. But I will still be releasing episodes of The Guide to Space. I know you've still got your Ask
Spaceman is going to keep churning out, of course.
And I think we've got a couple more collaborations planned.
We've got some collab videos lined up.
Yeah. So it's going to be a good summer. So don't worry, we're going to keep the content coming, but
just not this content.
Just not this live show. And then we've got
rewatch it. You can watch this stuff again.
Yeah, we've got years and years if you want to go back. And but no, and we will be sort of looking to improve things. So we've got some big ideas. A bunch of us have been talking. We're going to try and figure out some ways to kind of make a better experience. That's sort of one of the great reasons to take the summer off. And the whole reason, so this is leading up to the Weekly Space Hangout crew, which is the wshcrew.space. This is the place that you're going to want to go to be able to join a bunch of the people and, hang out over the summer and keep everyone entertained. And it was actually created because of our hiatus. So if you want a place to go and hang out with your space friends, this is the place you're going to want to go. Go to the wshcrew.space and join in there, and then you can just kind of keep the fire going until we're all back in the fall. Dr. Paul Metzetter, now, 1, where do people find out more? And 2, how do they contribute to you financially?
Excellent questions. So they can find out more on my website, pmsutter.com, as links to everything I do, including my social media, where you can find me at Paul Matt Sutter on Twitter and Facebook. One of the biggest things I do besides the Weekly Space Hangout is my podcast, Ask a Spaceman, askaspaceman.com, where you can keep flooding me with questions, and then I will devote 20 to, I think my longest episode was a 3-parter, so that counts as
on one question,
on one topic,
right?
One topic. It was a 3. That was fun. That was fun. I tried to limit those, but because there is a temptation to dig deep into every topic and turn it into a multi-part series. But all my education and outreach activities, none of it is funded by any institution that I work for. I do it all on my own, and it's all supported by you, by the listeners, by the audience. And you can go to patreon.com/pmsutter to find out more and how it supports everything I do. Everything I do that I do public facing, I give away for free. And I do ad-free, and I just ask for some contributions.
Wonderful. Now, I showed this in Astronomy Cast, but I actually forgot to show this to the Weekly Space Hangout crew, the Space Hangout. Check this out.
What is it? Was it your... Oh, yeah.
So this came in the mail. Whoops. All right. This came in the mail.
Wow.
Boom. Check it out. So we passed 100,000. I think we're like 112,000 now.
Oh,
so,
look at you.
There you go. So thanks everyone who has subscribed. Someone said it was great. Like someone in the comments was, I know it was really hard for me to press that subscribe button and really easy for you to make all those videos, but
Struggle is real.
the struggle is real. It's worth doing. So thanks everyone for subscribing and all of the support over all of these years. Here's to the next million, and I look forward to Paul's going to get one too. Just a matter of time. So go make sure you go.
Yeah,
over
a long time. So maybe Phantom Energy with the universe apart.
right
Before I
in
get
Google years. No, it'll come fast. Don't worry.
That's
All right. Well, hey everybody, have a great summer. And don't worry. We'll be back in a couple of months and better than ever and well rested.
And I'll be there too.
Right on. We'll see you guys later.
Take it easy.